Hi everyone, welcome to this lesson. We are going to look at electron structure in this lesson, and it's sort of an introduction to understanding how to write electron configuration, which is a really important skill that we need to have for this unit. But we're going to start off by understanding where electrons live in an atom. So really understanding what is an energy level, this is an important term, and what's an orbital, and where do they live? Where do these electrons live when we're thinking about any particular atom or even an ion as well, as we'll deal with in this course. And up until now in Science 10 we dealt with Bohr diagrams, which you might recall. And Bohr diagrams are really great for thinking about where electrons live, and they work really well up to about the first 20 atoms in the periodic table. And if you remember Bohr diagrams, we used to draw the nucleus, and then for example, if we're thinking of something like helium, which has 2 electrons, then we would draw the first shell, and we would place those 2 electrons in that first shell. And then the next shell would be drawn, and it could have up to a maximum of 8 electrons. And these Bohr diagrams, while they're very useful and they help us understand how bonding works between any 2 atoms, they are a simplified model of where electrons live in an atom. So what we actually know is that electrons don't really zoom around at these fixed orbitals around the nucleus, but in fact they live in really specific regions of space around the nucleus. And I'll give you a quick picture right now of what that looks like. So if this is the nucleus of an atom, for example, helium, for example, is a good example to use because it's really simple and it's got 2 electrons in it. So there's various energy levels, and as you can see, the energy is going up here. So if you think of these like little, these are orbitals, or essentially little regions of space where electrons can live, and they don't randomly live anywhere, but they actually start by occupying the lowest levels first. So in the case of helium, for example, we would have 2 electrons here in the very first level, and we actually draw them in like this rather than little dots as we did before in the Bohr diagrams. And I'll talk about that later. That's not really important to us right now. But each orbital can hold 2 electrons. So this is a much more realistic picture of where electrons live in an atom. And if we were dealing with an atom other than helium, so something that has more electrons, for example carbon, and it has 6 electrons, carbon would then have 1, 2, 3, 4, 5, 6. And so we'll talk about the rules in a moment of how these electrons fill up. But what's really important here is just getting a picture in our head about what energy levels look like and what these regions of space would look like. And we're going to get more in depth here and understand this a bit better in a moment. When you look at your periodic table, you can tell how many electrons any given atom has just by looking at the atomic number. And we're used to doing this. So for example, if we think about carbon, how do we know carbon has 6 electrons? Well, one is you could count its placement in the table. So 1, 2, 3, 4, 5, 6. You could do that. Or you could notice that its atomic number is 6, and that tells us the number of electrons as well as the number of protons in a neutral atom of carbon. So the atomic number is really, really important to us. So carbon has 6 electrons. Now, that's all this periodic table tells us at the moment. We can't, looking at a periodic table from what we know so far in Chemistry 11, we wouldn't be able to say where in particular those 6 electrons lived around the nucleus. But that's what we're about to learn. So there's some really important terms that we're going to define and understand in simple terms for us, so that when we can talk about where an electron lives using these terms. And the first term is energy level. So energy level is basically exactly what it sounds like. It's the amount of energy that a specific electron has. And here's our actual definition. It's a specific amount of energy that an electron has in an atom, or also in an ion, but we'll stick with atoms for now to be simple. And we usually use this letter N to represent the energy level. So for example, if N is equal to 1, that represents the first energy level. We also have n equals 2 and so on. Okay, going all the way up to n is equal to 7. So there are a total of seven energy levels. So 7 in total of possible energy levels where an electron could live. So going back to our this is an energy level diagram, and here we can see the different energy levels. So n equals 1, for example, is right here. If I draw this right into our energy level, n equals 2 would be here, n equals 3, including the 3d orbital here as well. We'll talk a little bit more about these orbitals in a minute, but you can see that the n value is increasing as we go up in energy. So n equals 1 represents the lowest energy level, and n equals 7 way up here, and it's not even on this. This is more of a simplified energy level diagram. It doesn't show all the levels, but it would go all the way up to n is equal to 7. If in fact we had an atom that had that many electrons to occupy that high level. So, and electrons start occupying the very lowest levels, and our periodic table is actually set up to let us see really clearly which energy levels electrons would occupy, and also what orbitals they would occupy. What is a quantum of energy? This is another term that we see in the textbook, and we use it a little bit in this course. Quantum mechanics is a big area of chemistry that is definitely beyond the scope of Chem 11, but if you carry on and do a degree in chemistry or in science, you might actually take a course about quantum energy and quantum mechanics. So, but a quantum of energy is essentially just the difference between energy levels. Okay, so if we think about any two energy levels, so for example, the difference between n equals 3 and n equals 2, the difference between here would be known as a quantum of energy. Energy. And so electrons give off energy when they jump between energy levels. And so that we use this word quantum to just define that difference in energy between any two energy levels. They can also jump up in energy level as well when they're excited. An orbital, this is a really important term. We're going to be using this a lot, so we want to be clear on what that means. So an orbital is really the region of space where an electron lives. And what I mean by that, if I come back to my energy level diagram for a moment, okay, this is an orbital right here. An orbital is a space, it's a spot where an electron can occupy. And so there are different types of orbitals, and an orbital can also hold a maximum of 2 electrons. So the different types of orbitals refer to the letter that we use to define it. So there's an s orbital, which you can see here. There's there's different ones. N equals 1. There's a 1s, 2s, 3s, etc. There's also p orbitals, and there are d orbitals, and then finally there are also f orbitals, which are not shown on this diagram, but they exist. So there are different types of orbitals, and let's write those out for a moment. So we've got the s orbitals, and an s orbital is just one orbital, okay, that can hold a maximum of 2 electrons in total. And there are s orbitals at all the different n energy levels. So n equals 1, n equals 2, all the way up to n is equal to 7. Okay, these all have s orbitals. There is also a p orbital. Okay, p orbitals. Each p orbital has 3 orbitals. So there are 3, okay, for any given p orbital, and each every orbital can hold 2 electrons. So in the p orbitals, it can actually hold up to 6 electrons because there's 3 of them. And if we look at our chart for a minute, everywhere we see a p orbital, you'll see that there are, or I should say a p, these are called this will be called a subshell, but there's 3 p orbitals here, and if I look here at 3p, there's also 3, and 4p has 3, so every p type would have 3 orbitals. Okay, and p orbitals exist starting at the n is equal to 2 level, all the way up to n is equal to 7, but there are no 1p orbitals. So p orbitals start at 2. Then there are d orbitals. D orbitals, there are 5 d orbitals. Sorry, this should say d, not 3. Apologize. And each orbital can hold 2 electrons, so in total there can be up to 10 electrons within those d orbitals. And d orbitals start at n is equal to 3. So there are no 2d or 1d orbitals. It starts at 3d. And then finally, the last type of orbitals are the f orbitals. And f can actually hold up to 14 electrons. So there are 7 orbitals here. 1, 2, 3, 4, 5, 6, 7. So if we were to have an atom that had a full f orbital, or I should say all the f orbitals here were full, it would have a total of 14 electrons. And the f orbitals start at n is equal to 4. So there are no 3f, 2f, or 1f orbitals. So that's sort of an overview of what is an orbital. A shell then, a shell and a subshell are just 2 other words that we're going to throw around a little bit in this unit. And so a shell then, if we're talking about a shell, we're talking about a set of orbitals that have the same n value. So for example, if we think about n is equal to 3. Okay, n equals to 3 that's an n value. That's the 3rd energy level. And so within n equals 3, there is 3s, 3p, and 3d. Okay, so we would say that all of these, the 3s, the 3p, and the 3d orbitals, because they all have the same n value, and they're all the same energy level, or they all have the same n energy level, this would be a shell. A subshell then would be the orbitals within a specific type. So a subshell is a set of orbitals that are all the same type. So for example, the 3p orbitals. So right here, if I look specifically at the 3p orbitals, okay, each one of these 3 orbitals all belong to the same type, 3p, and so we would call that a subshell. So that's the difference between a shell and a subshell. We'll come back to those terms as we use them. So let's go ahead and pick an atom to look at, and we're going to look at how its electrons are arranged within that atom, so where they live at the different energy levels. And then we're also going to look at the periodic table and find and label that periodic table with all these different energy levels and orbitals, so that we can use it later to figure out the electron configuration of any atom or any ion. So we're going to start by let's start with a fairly simple example. So let's look at the difference between hydrogen and helium. And let's do hydrogen first. So hydrogen on our periodic table is right here, and it has 1 electron. And this is n equals 1. And so its first electron is going to live in the lowest possible energy level, which is right here at n equals 1, and it would occupy the 1s orbital. And so we could go ahead and put our 1 electron in right there, okay, for hydrogen. Helium, on the other hand, on our periodic table, helium is over here, and it has 2 electrons. And you might also remember that helium is part of the family called the noble gases. All of these atoms in this column, in this family, have full valence shells. Full valence shells just means that in its outermost shell, the shell is full. So there's the maximum number of electrons exist in that shell. And here for helium, because helium is in the its electrons live in the 1s orbital, and that 1s orbital can only take 2 electrons, so it's full. This actually makes it very, very stable compared to hydrogen. So if we come back here for a moment and we think about helium, helium would have 1 more electron here, and that means that it has a full shell. Its 1s shell is full, and we actually later on we'll learn to use this type of notation, but we actually put a little 2 here to represent that there are 2 electrons in that 1s orbital for helium, and it is full. So it's very stable and doesn't want to react with anything because it doesn't want to take any more electrons and it doesn't want to lose any. If it lost one, then it would have not a full shell, and if it gained one, it would not have a full shell either in its outermost orbital. So it's not happy to do that, which makes them very unreactive, the noble gases. Hydrogen, on the other hand, with only having 1 electron, is quite reactive. It's quite happy to bond with a number of different atoms because it could either gain an electron and become stable, or it could lose it altogether, and it would also be stable because it wouldn't have any electrons. Let's think of an example that has more electrons than either of these two. Let's go ahead and pick an atom that is got quite a few electrons. So let's pick sulfur, for example. Sulfur, if I circle sulfur, sulfur has a total of 16 electrons. So if we came to our energy level diagram here and we were to fill in for a sulfur atom 16 electrons, starting at the lowest energy level, which would be the 1s orbital, and we were to put 2 electrons into each orbital, it would look like this. If we count them together, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And this would be the electron configuration of a sulfur atom. It would have 16 electrons, meaning that the outermost subshell that we have here is 3p, and it has a total of 1, 2, 3, 4 electrons in that 3p subshell. So we could write the electron configuration, which we will learn in a moment how to do. Notice that using an electron or an energy level diagram and populating it like this would be very time consuming if you were to do this all the time. And so this isn't that good of a strategy for us figuring out what the electron configuration is for a sulfur atom or for any other atom that has many electrons. So instead, what we'll do is we'll learn about electron configuration, which is a simplified way to show how many electrons live in an atom, okay, or where they live specifically. So what is the configuration of electrons within an atom or in an ion? And to do that, we're going to need to know how to use our periodic table to figure out where the different orbitals are on our periodic table. So we're going to go ahead and label that now together so that we can use it in the next lesson. So I'm going to get you to go ahead and get out your periodic table that you've printed out and that you're using in this course, and we're going to go ahead and label it right now. And it's really easy once we get the hang of it. So the first thing we're going to do is understand that when we're looking at our periodic table, the energy levels are increasing, going down. Okay, so when we're just starting at the top, we're starting at the lowest energy level, which is n is equal to 1, which makes sense because the number of electrons are increasing as we go down the table. Now, in your Hebden textbook, if you look at page 155, there is a nice diagram without all the elements in there that shows where the different orbitals are within the periodic table. But if labeling them right on your periodic table is really handy as well. So the first one here is the 1s, which is right here. Okay, so this is the 1s. And it also includes, over here, helium is also part of that 1s. Its electrons live in the 1s orbital. The next one down is 2s. And 2s, all of the s orbitals, can hold a maximum of 2 electrons. Okay, so lithium, for example, has 1 electron, and beryllium would have 2 electrons in the 2s orbital. Coming across and over to the other side here, okay, this is the 2p, starting right here. And I think what I'll do is I'll actually write it over here just for simplicity. So we won't write it there. So 2p starts at boron and it goes all the way to neon. And the 2p can hold a total of 6 electrons. Okay, all of the p orbitals can hold a total of 6 electrons. The next one, coming over here, we're going 1, 2, 3. Now we're at 3, so we're at the 3rd row. And that's the 3rd energy level. So sodium and magnesium have electrons in the 3s orbital. Okay, and then coming across here, we get to the 3p's. So the 3p orbitals here, again, total of 6 electrons. Notice that this is really handy and it's really easy to remember. You don't have to remember that there's 6 electrons. If you count how many elements are in this 3p section right here, there are 6. 1, 2, 3, 4, 5, 6. So that makes it very, very easy to remember. The same is true of the s orbitals. Okay, if you look at here for 2s, there are 2 elements and there you have up to 2 electrons there. Okay, the next one before we move on to 4 is the 3d orbital, and the 3d orbital actually starts right here, okay, at scandium, and it goes all the way to zinc. So these are the d orbitals right here, okay, and the d orbitals contain a total of 10 electrons, which will be easy to remember because there are 10 elements within there. Okay, and so if I'll write it right down here, but 3d starts right here. Okay, coming over here then, where potassium and calcium are on our periodic table, the electrons there occupy the 4s orbital, and there's 2 there. So it goes 4s and then 3d, okay, and then 4p right after that. Oops, 4p, sorry. Okay. Okay, so from now on it's pretty easy. We're just going to keep labeling it. So rubidium and strontium are 5s. But notice the d orbitals, because they start at n equals 3, when you're looking across your periodic table, the d orbital that follows the s orbital is always going to have 1 energy level lower. So this one is the 4d. Okay, all the way to cadmium, and then we get into the 5p. Okay, 6s is here. I'm going to speed this up a little bit. 5d starts at lanthanum and it goes all the way down here to mercury, and then we have 6p. And you notice on your periodic table that you have this little line that shows that these elements actually exist in between lanthanum and hafnium here. So if you see the jump in the atomic numbers from 57 to 72, down here is actually the f orbitals. So these elements down here have electrons in the 4f orbital, and here is the 5f orbital right below that. Okay, finally we get to the last energy level in our periodic table, which is 7. 7s is here, 7p is over here, and finally we've got 6d. Right here, the transition metals that live in the center there. Okay, so you've got it labeled now, and and it's when we're going to move on in a moment to a lesson on electron configuration. But one of the things that you will notice is if you look at the the energy level diagram. If I just clean this up a little bit, if you look at the the energy level diagram, and you look at the order in which you see the orbitals as they go up in energy, right? It goes 1s, 2s, 2p, 3s, 3p, but then it's 4s before 3d. And sometimes students go, oh boy, do I have to remember that? Actually, no, your periodic table will remind you of that. So if you look here, for example, the 4s orbital is at a lower energy than the 3d orbital. Even though the number 3 does come before the number 4, if you look at your periodic table, you'll see that that's true. Here's the 4s orbital right here. So if we were filling up the electrons for potassium, for example, okay, that has 19 electrons, we would start filling the 1s, and then the 2s, and then the 3s, and then all the 3p's, and then the 4s before we started filling the 3d orbitals. So when you read your periodic table from left to right, it actually shows you the order in which you should fill the electrons. So there's really no special rule that you have to remember that 3d comes after 4s, because if you look at your periodic table, 3d comes after 4s in the periodic table. So if you follow, if you can remember where these orbitals live in your periodic table by either writing them on, then you're going to be in really, really good shape when you start to write out electron configurations, because it just simply follows exactly where you've noted them in your periodic table. So that's just something that will help you in terms of figuring that out. Great, so take a moment and make sure that you have labeled these orbitals on your periodic table. This will really help you as you get going. Eventually you'll probably be able to have a clean periodic table and write them in on your own, but for a test, for example. But for now, label your periodic table so you can work through some of the questions in the next lesson with electron configuration.